Everyone, welcome back. So now I have the pleasure and privilege to welcome you to the second half of Polyoxometalate Gyan course. And as I mentioned in the scope of the course, in order to increase or broaden the perspective of this course, we have been able to invite Professor R.N. Mukherjee, who is a distinguished inorganic chemist, and I would like to give a very short introduction about Professor Mukherjee, though all of you know Professor Mukherjee very well from his work and from his accomplishments. So Professor Mukherjee is currently, as you know, is the director of IISER Kolkata, and he is also professor of IIT Kanpur. He's serving there, and he has been a postdoctoral associate with Professor Dick Holm, and that's where Professor Craig Hill and R.N. Mukherjee, they share their teacher, so to speak. And he was in IACS before that. He did his PhD with Professor Animesh Chakraborty, and he has been recipient of several prestigious awards, and more importantly, he is now the fellow of all the academies of India, as well as Royal Society of Chemistry, and is a member of the editorial board of Inorganic Chemistry, the most prestigious journal, you know, Darjan Transactions, and others. And he is a J.C. Bose fellow. So it is perhaps a privilege for all of us to have Professor Mukherjee talk about broader aspects of inorganic chemistry, and I have requested him to give a talk about perspectives on inorganic chemistry, and his talk today is hydrolytic enzymes, molecular level understanding. So with this, I would like to request Professor Mukherjee to please come on stage and give the lecture. Thank you.
Colleagues from this institute and the dear students. You know, it's a Gyan program and polyoxometalate, and I do not work on polyoxometalates. That is my limitation. I am basically by training a coordination chemist per se. In fact, I play with the metal ion and the ligand, with the bioinorganic chemistry pointing towards that, and also a lot of things, metal, radical, a lot of things. But this is one of them is the hydrolytic enzymes. And to tell you how much time I have, 1 hour. So the main thing which I had in mind is that the way I designed my research career, as has been mentioned, after my PhD and a postdoc for some time at Harvard, the main thing was do science at a molecular level understanding of a complicated biological processes. The two things are very important. You have a metal ion, is a metal containing protein or enzyme. So there is some place where all the actions take place, and it is surrounded by the amino acid side chains, the protein peptides. Now the whole thing, if you try to understand at a molecular level, you have to more or less copy that portion called the active site where the main reactions take place in your laboratory outside protein environment. And once you do that, then you make a compound which will have some relevance to the active site. And in the active site, because of the complexity of the protein or enzyme, you will not be able to pinpoint a very minor or very tight or very intrinsic some properties which is difficult to control in a very big molecule. So once you pay attention to, focus your attention to a particular place, and I am very, very fond of paying attention to the synthetic analog approach of biomolecules. So synthetic analog approach to biomolecules means you design something outside protein environment with your knowledge of inorganic chemistry, could be organic chemistry, because could be bioorganic, could be bioinorganic, whatever your expertise would allow you to excel. Now my training had been in inorganic chemistry, and I always believe in that there will be some metal ion and the ligand. Whatever you do, radical chemistry, supramolecular chemistry, organometallic chemistry, bioinorganic chemistry, it is basically the love story between the metal ion and the ligand. So ligand and metal ion will be having some interactions and then you have to exploit it. So let us say these hydrolytic enzymes was the title of the molecular understanding. Once you have achieved that, then only you know what you are talking about. So first is hydrolytic reaction. So first thing is, all of us we had our lunch. So we ate something, I don't know what you have ate. I did not eat at all. I did not eat at all any non-veg, only vegetarian. But whatever it is, something has gone inside. Could be some carbohydrate, could be some protein as well. So whatever you have, big molecules, you should break down to smaller one. So you have to break down to the smaller one. That means, basically by very many means called hydrolysis. You must have heard the name of carboxypeptidase, okay? And you must have heard the names of many other hydrolytic enzymes. So what is hydrolysis? Very simple. Class 2 knowledge, you don't have to do any research. Addition of water to a molecule, that is hydrolysis. But it is very easy to say, and understanding is not so easy. As for example, hydrolytic reactions may general considerations. What? This is I will try to do. Structure and function of hydrolysis, some selected examples. And models are very important so far we are concerned. Strategies to follow. From this knowledge, what strategy you will adopt to duplicate some of the functions. And also structures and chemical reactivity you have to correlate, because structure function is basically chemistry. And then you have a rate or mechanism of, as we are talking about hydrolysis, there should be some rate, there should be some mechanism by which these big molecules are getting hydrolyzed. That's the bottom line. Now general considerations, hydrolysis, I told you, cleavage of bond by addition of water molecule. Very simple. I recall long time back when I was a graduate student, undergraduate student, Bachelor of Science I was doing in chemistry honors. I was given ethyl acetate to hydrolyze. What do? You put some sodium hydroxide, you boil it up, it will just become, it will break down the ester, and you know exactly and analyze, and you know what you have done. But nature is not that. Nature has specific enzymes to catalyze these hydrolysis reactions, like they are called hydrolytic enzymes. These enzymes have evolved to hydrolyze some of the most important, like proteins, phospholipids, DNA, to name a few. Take an amide. So you have the amide bond and put water. So should be, here is the bond. So this bond should be clipped, and by definition of chemistry, all of you know, bond breaking and bond making is chemistry. Just to make is not chemistry. You have to understand, you will break, what happens. Or you put together, because the heel is here, you have to water, you break down to H2O and O2. Or combine to generate the water. Bond making and bond making, or reorganization of electronic charge density is the definition of chemistry. So you have that, but you take this reaction and put a equilibrium sign, it can go this way or that way. Then the question is, then a little bit of physical chemistry, rate constants and things like that. So you have the uncatalyzed reaction is very, very slow. It will never go to that side. Once it is formed, it will remain like that. The rate constant is -11. So you know diffusion limit almost. So it's a very, very sluggish process, doesn't hydrolyze at all. But the reaction can be catalyzed by some enzyme named carboxypeptidase A, and it's very fast. -11 becomes 4. It is 4. So you know the enormous amount of rate enhancement takes place because of some molecule in biology called carboxypeptidase. Now we should understand what is that, how does it look like, the active site structure, and can we understand that by making molecule in the laboratory. Then I already said generation of energy from oxidation of foodstuff. I said that your lunch molecules in food are broken down into smaller units. Proteins are hydrolyzed to their 20 kinds of constituent amino acids. Polysaccharides are hydrolyzed to simple sugars, glucose, and fats are hydrolyzed to glycerol fatty acids. This is going on all the time. So hydrolysis, if it doesn't happen, then we cannot process the food. And finally, food has to be oxidized, which is your metabolism, right? Food will be oxidized, you generate a bunch of electrons, use those electrons to reduce oxygen to water. From time to time, you have to release water from our body. And the generation of water is connected to the synthesis of adenosine triphosphate. So more and more adenosine triphosphate you generate, you have to generate in your body oxygen, electron, 4 electron, 4 proton to make 2 molecules of water. And that's why oxygen reduction plays a very, very important role in the enzyme named cytochrome C oxidase. Now you will know, so this is the basically important thing. Now you will find there are 200 roughly, when it is more, 200 metalloenzymes. In all those enzymes, only one metal ion is present. The name of the metal ion is zinc. So zinc is present in all hydrolytic enzymes. Now what is so special about zinc? These are the points. There is an article, you know the name of the students, not the teachers I am saying. William Lipscomb or Bill Lipscomb. Have you heard the name? You have not heard of. In the school level you have read banana bond, you know, B2H6. So he got Nobel Prize for that, William Lipscomb. So he got Nobel Prize for B2H6, but he is the man who did large number of these hydrolytic enzymes, particularly carboxypeptidase. Few years back he died, and he is a very, very well-known biochemist that way, protein crystallography. And his boss was, any idea? You don't know. His boss was actually Linus Pauling. So Linus Pauling and then Lipscomb. So then the thing is, why zinc is so great? You have to do hydrolysis. Flexible coordination geometry. This is our undergraduate BSc, undergraduate course, D10, 5d orbitals, each one having 2 electrons, so spherically symmetric. So zinc 2 plus ion does not go for a preferred geometry. Whether tetrahedral, square pyramidal, Chiron bipyramidal, octahedral, everything is okay for zinc. That is the beauty you have. Fast ligand exchange, kinetically labile. That means a metal ion a bond is being formed, after some time bond can be broken down. If your bond formation and bond breaking is too sluggish, then your compound will be formed, nothing will be liberated. So catalysis is the one thing where you do a reaction, it has to liberate. So you have fast ligand exchange is a good thing. And this is our undergraduate experiment, Lewis acidity. Greater the Lewis acidity, greater is the charge density of the metal ion, and greater will be the ability to activate the water molecule complex. What is the meaning? You start from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, D0, D10. What happens? The size is becoming smaller and smaller. Take all of them plus 2 charge. So take plus 2, and divide by their size. What will happen? The zinc will be having maximum of this kind of Z effective by R, that ratio. The maximum value means best Lewis acid. So zinc is the best Lewis acid, and that is one of the reasons why nature had chosen zinc 2 plus ion to do the job of hydrolysis compared to other metal ion. Now zinc is present, smaller size, so that means effective positive charge on the nickel ion, zinc ion is the maximum. Then you have a water molecule. So now if zinc would like to pull a lot of electron density, then this water will become weighed quickly. So metal coordinated nucleophile will be generated, and metal coordinated nucleophile can attack for the job of hydrolysis or carbon dioxide processing to bicarbonate ion, carbonic anhydrase. These are all connected. So then, intermediate polarizability. You know polarizability meaning. Polarizability meaning means you go down, you can manipulate. You go up, you cannot manipulate. You oxide and you go all the way down. Strong binding to suitable sites and lack of redox activity. No redox processes. D0, D1, D2, D2, this thing doesn't happen because you have D10. So no redox property. So this is the thing, and these are written by Lipscomb in Chemical Reviews, 1996. Oh, sorry. So now, the point is selected examples I will give. So carbonic anhydrase is the one, which you have zinc. Carboxypeptidase also zinc. Urease, nickel. Perchlorate phosphatase, iron, some other metal ion, manganese, iron. So let us go one step by step, the enzyme. So this is very, very important. Carbonic anhydrase. It is very simple thing. You eat food, process there, so you have broken down to small, then they will be moving to your body cell. Now you have to process the food. How do you do it? You have to oxidize. So if you generate oxidation here, you generate carbon dioxide. So your skin will be bulging out because a lot of carbon dioxide is being formed. But that should not happen. You are walking after some time, huge thing. What happens? There are a lot of carbon dioxide. So carbon dioxide has to be processed. So carbon dioxide is processed by the enzyme named carbonic anhydrase. How does it do? There is zinc ions are coordinated by 3 histidines. So 3 histidines and 1 water. You take these histidines and water, it becomes OH. As I told you, it pulls a lot of electron density. In the process, OH bonds become weak and you have OH. So that is the metal coordinated nucleophile. That is the active form. And your reaction is this: CO2 should be processed to form H2CO3, but H2CO3 is also not soluble because you have the cold rings always under pressure. So H2CO3 should be deprotonated to generate bicarbonate ion, which is soluble at physiological pH 7. So this thing goes on. How does it function? So you have this, then you have that. Now what you do, you think of that, CO2 comes in, bond polarization, O minus, C plus, so OH minus will attack, and then after that it's not a big problem to understand. So you basically generate this kind of bicarbonate ion liberated, and the process can repeat again and again. Bottom line is only one thing: metal coordinated OH ion and bond polarization attack nucleophilic, and things will be over. This is for carbonic anhydrase. All right, this is fine. Let us go to other one. This is the other one is carboxymetalates. The same story. What is that? You have a zinc, 2 histidines, 1 glutamic acid, and you have an OH coordinated. This is the active site structure, structurally characterized. And you have a, glutamic acid there is a hydrogen bonding interaction. There comes the so-called supramolecular interaction, non-covalent interactions. So this is your covalent bond, and that portion is non-covalent bond. What is non-covalent bond is doing? At that stage, they are very nicely happy, lined up. The substrate comes in. Your substrate is the peptide. So it comes in. What it will do? If the medium is pH 7, carbonyl group will coordinate because it will not generate N minus. It's not alkaline. So CO coordinates, and this is like this. Then this is here. Then you know they are nicely placed. Because of this coordination, electron density will be towards that this place will be positively charged. And that place and this one can talk to each other and form a bond. This is the intermediate can form, and then you have all kinds of bond cleavage, and you know at one point NH2 will be liberated, another point acid will be liberated. So the bottom line is whatever be the details enzyme, the same story. Metal ion, water, then metal ion, OH ion, substrate gets bound, OH ion attacks, and liberation of the product, and this cycle repeats. So this is done by Perkin from Columbia University. He wrote a review article. So these are the zinc subs 2 roles, activating the water towards deprotonation by a glutamate residue. This glutamate residue, when the water was present, pulling electron density, OH and H is water. So this water is pulling electron density means this proton will go to that, so it becomes OH. So this non-covalent interaction is changing the acidity of the water molecule. And then you have the usual process. And activating the carbonyl group of the peptide unit towards nucleophilic attack. Because if it coordinates like this, then only this attack will take place. So both are nicely matched. Then you go to the other one. So there are a lot of areas. This is we did. Electrophilic activation, metal hydroxide nucleophile. You take the colored one. Metal coordinated OH ion. This is your substrate. Substrate gets bound, and this metal coordinated OH ion attacks. That is our more or less the pure focus of everything. This is a review article written some time back. I'll go show you some dinuclear centers, which is the metallohydrolases, dinuclear. You check these ureas. You know this is the first enzyme to be crystallized out in 1932. Structures was analyzed later on, much later in the 80s. So the structure came in 1997, but before that also. What you have the structure? You have the reaction is you have urea and generate CO2 and ammonia. There's the break the bond. And you have nickel, and you saw this is histidine, this is another histidine, so both of them. And that nickel also has histidine, that has also histidine. But this nickel has one aspartate, this nickel does not have. It has a water, there is a hydroxo bridge, and there is a lysine carbamylated. It is a bridging. So this group is bridging the two, and hydroxide ion also bridging. So it is a very rigid bond. But this nickel has one water, nickel has one water in a cis position. Okay, the typical cis. Why cis? You will understand very soon. Because what will be the job, and the distance between this and that is around that. What happened? This is important. One place substrate will get bound, and here wedge will be generated. You know, electron density will be pulled by the metal ion, so water will become wedge. So substrate, decline. Oh, how do you do? I have already spoken. So this is the thing. One nickel ion is further irrigated by, as I have said. So this one is 1, 2, 3, 4, 5, and this is 6 coordinate. You must have a vacant coordination site, otherwise substrate cannot form. If your compound is 6 coordinate, that compound will never do any damn thing. So your compound should be coordination flexible. So as far as coordination flexibility is concerned, is a very important issue. Then you have purple acid phosphatase. You know, in Bengali we call it ramalu. That is called the sweet potato. The sweet potato has an enzyme called purple acid phosphatase. What it does, it also does the phosphate ester hydrolysis. What? You have an iron 3 and the metal 2. The iron 3 has tyrosinate, and these enzymes, you can, as I taught in IIT Kanpur, it's very easy. Iron 3 enzyme